So anyway, there's good, bad, and ugly linear congruential generators. So what about more sophisticated pseudo-random number generators? I told you already. Here's the Mersenne twister. And the Mersenne twister has a period of 10 to the power of 6,000. It's a very, very big number. So that's basically the default in most packages. Okay. Should we lower one of those things? Is it too? Okay.
You can switch off the light, maybe.
Oh, which lights? You know?
I think it's the one on the right side.
This one?
No, on the right side of the door.
Oh, here.
But then everything.
Oh, that's not good. Oh, well. Anyway. Okay, so, whatever, 623 dimensionally distributed pseudo-random number generators, and I just want you to be aware that it has its limits as well, and there are people studying simulations that go around it. But I'm not too worried because when you do these kinds of simulation studies, usually it's done with the decision person on board. So usually it'll be an engineer or whatever. So it's not done like some black box thing. It's usually there are human operators. Okay. So this is what I wanted to show. So if I say question random stuff we've been using, it tells me this is where it is, my path. So I can just CAD it, and so you can just see exactly what it's doing, and yeah, this is where all of this is coming from. Okay, let's do some warm-up before simulating a drunkard's walk. So it's a little more interesting. So we have to use this cum sum function, which we kind of did when we defined the distribution function, the cumulative sum. So it's a numpy cum sum, or PyLab does the same thing. So from numpy import cum sum an array. This is another way to import. Before we were doing from import numpy as np. That's one way to go. Then you can call anything in numpy. Here we're explicitly importing cum sum an array from numpy. So now the namespace cum sum will replace any other names with the same characters, right? So this is a cum sum array, range 0 to 10. So you see the array is just 0, 1, 2, 3. Here you get the cumulative sum. So as you keep going, it just accumulates the sum. Yeah, so you can do the same with PyLab. We can convert this using the toList method to a list. This is often handy. You want to use list methods or list of cum sum range 10. So then, say you have some probabilities in a list and we want to get the cumulative sum of them, then we can do it like this. So let's say there's P left, probability of say going left, and P right is probability of going right. Let's say that's quarter and a quarter. So we're just assigning it to those two variables. And then I can then do cum sum P left, P right, and convert to a list. So now I have the cumulative probabilities of going left or right. I've left the remaining part of the probability for up or down. Yeah, so you can work with lists as well as tuples. So this is what we're going to try to do, simulating a drunkard's walk. So we're going to essentially take numbers from the uniform 0, 1 random variable, pseudo-random numbers, and somehow use them for this purpose. So the mathematical model of the walk is that the drunkard has no idea where she or he is going. At each decision point, she makes a random decision about which way to go. So So we can just think of being in Manhattan with streets and avenues. So it's like a grid. So you're just somewhere, and then if you're drunk and you go left or you go right. So you're just walking along the avenue. And we can say 0, 0 is where the drunkard starts, right? That would be our starting point. So we already did this. This is how to pack and unpack tuples. So here I've already packed it, and then I'm unpacking it. So this is some point x is 3, some point y is 2. So we can keep track of these integers that come from accumulating these random walks. So here is a little function. So this is kind of a pedagogical thing. So later on we'll do this all a bit nicely. But for now, let's say we make a function called make left turn point. And this function takes as argument a list of points. Okay. And the tuples in the list represent points in a 2D space. So the destination of a left turn is a tuple representing a point, which is on a 2D axis. It would be to the immediate left of the last point in the list. So here is the new point. Let's say we start at the origin. So also the default return value. And then if the list of points is more than 0, then we do the following. We say the last point x and the last point y is simply the final element in the sequence. Right? We grab the last element in the list. So this likelihood of list minus 1 tells us that's the index. And then we say that's our last point. Now we have to generate new points. So new x is just last point x minus 1, because we're just simulating a pure left turn in the x coordinate. And then our new point is going to be new x and the last point in y, right? Wherever y was is still the same, and then we return a new point. Okay, we do exactly the same for the make right turn, right? So except we do a plus here. So we can have lists of functions in Python. That's nice. So I can have movement functions is a list of make left turn point and make right turn point. So, and then I can ask what is the type of my first element. It's a function, and so it will be the second one. So we can take some path, which is represented as a list of points in 2D, and try to find the point that is the right turn from the last point in the path. Right. So what will that be? Last point is 2, 0. So on x coordinate you're at 2.
Sometimes square matrix length or sometimes length of.
I think I'm asking 3, 0, right?
Mm-hmm.
I mean, I'm just saying, if you have a path, you're going to have a bunch of points, and the last point is here 2, 0. And then if you want to make a right turn from it, that's what I'm asking. Yeah. So yeah, I'm just sort of trying to pull this thing apart a little bit. So now I can do movement functions of 0. So that's the first function, right? So this will give me so the first one is what is the left turn, right? Make left turn point. So this will give me a left turn from here, right? So 2, 0, the left turn from 2, 0 will take me to 1, 0. Oh, yes.
Why do we want to put functions in this?
Why?
Yeah.
because I can do amazing things, right? I can have a list of functions. Each function will do various things, and I can call each function to operate on my sequence of paths I'll be doing. So for example, right, we're just going left and right. So the assignment asks you to go left, right, up, down. And the challenging assignment asks you to go left, right, up, down, and then in the other direction as well. So you can easily generalize to a drunkard walking in 3D in Manhattan in the future, right? Go up and down. I mean, that's just for this example, but it's much more general. If I have a function, if I have a list of functions, I can apply, according to some random value. I can apply each function according to the pseudo-random realization. So I can do very general things. I can start moving through, graphs, and I can, grow trees, whatever. So it's a very general idea you want to.
Is it possible to have like a dictionary with functions?
Yeah, if you want, yeah, you can do.
Type up, down, instead of function like 0, 1.
Yeah, I mean, you can do whatever you want. I mean, I just thought I should introduce you to a list of functions from a syntactic point of view because it's quite powerful, right? Because I only need to access each function in this list according to the index. So if I have some operation that tells me, according to the pseudo-random number, if it's between such and such value, apply this function, the kth function in this list. Yeah, I mean, if you want to do it with dictionaries, that's fine. But then, what I'm doing is basically should be equivalent to a dictionary where the keys are just the 0, 1, 2, 3 things. I have not made a dictionary by the values of functions. I don't know. That should be possible, right? As long as the keys are hashable. You can play with it. But, I'm like a very American in my sort of philosophy here. It's very pragmatic. If it ain't broke, don't fix it. So I'm just doing like bare minimum. But this is a very powerful primitive for you guys to have under your belt, have lists of functions. Right. Yeah, let's do this. So let's see. Movements, function, dict. This is what you want to do. I have no idea if it'll work, but why not? Let's do this. Right? And then what should we do? So I made an empty dictionary. And then you want movements, function, dict. And how do we do the syntax? Is it like this? I'm going to call key 0 equals. This is what you want to know if it will work. Okay, let's see. Seems to be working, right? So yeah, you should be able to do. I mean, I don't know. Shit. Oh my god. All right, you can figure this out, right? It's not the point. Maybe having a dictionary of functions is a good idea, but maybe not, right? Movements. My keyboard has been crazy today, like when Tilo was here, I lost the keyboard. What's going on? All right, copy paste. Control C. So what does this make right turn point? Okay, so then what we're gonna do? We want to know. Oh, you see what happened? The cell was marked down. Okay, that was the problem. All right, and I don't know. You can look at the value and see if it's still a type function and play around. And maybe in some cases it might be useful to have a dictionary of functions because then you can do other things. All right, let's not get distracted because I have a lot to cover. I at least want to get to Markov Chains before 3:15 next Friday. So anyway, so here's movement function 0 of some path. So this is going to give me the left hop from the last point in some path. And then here is movement function 0 of some path. And now I'm going to append that new point to some path, and that's basically how I'm going to go, right? This is how I'm going to create my hops, left hop and right hop, by pulling the right element in the list of functions and applying it. Now that's all deterministic, so you can try and do the same thing with the right point. You try. So let's now say we have the probabilities of 0.25, 0.25, 0.25, 0.25. So I'm going to go left, right, up, and down is what I really want. And I'm going to turn it into a cum sum. Okay, so I have 0.25, 0.5, 0.75, and 1. And then what I'm going to do is I'm going to get samples from the uniform 0, 1. Remember, these will be numbers between 0 and 1. So if u, the sample, lands between 0 and a quarter, then we go left. If u lands between quarter and a half, we go right. For this, we go up. And for between 0.75 and 1, we go down. That's the logic. So I want you to basically simulate u. And then depending on where u falls in these 4 little subintervals, I want you to apply this function. Right, so here is the this thing. Now I want number of simulated moves to be 6. And so now I have PRNs, pseudo-random numbers, in this list, random for I in the range n. So this will give me 6 random numbers, uniform random ones. And then I have this for loop. So for u in this list, I look at if u is less than or equal to cum probs of 0, then I want to print u was this, so go left. And if u is less than cum probs of 1, I'll say u is such and such, so go right. So clearly out of the 6 samples, only 4 of them met the left and right conditions, right? So the others are ignored. Right? So I'm just giving you partial solutions, so your exercise is to kind of complete this later and show me. So now you'll see that we've only dealt with cases for left and right. So that's why we're not getting n lines of output, right? But then we can kind of expand on this a bit. So now instead of writing, the 2 cases, I can just loop through the cumulative probabilities directly, right? So I can loop through the length of this cum probs list. And then if u is less than cum probs of I, because I can just ask if it's in the first interval, second, third, or fourth, do this one if else statement, I will say this. So now you see, so u was 0.24 something, it's less than 0.25, so I go left, and then I'm just writing down, I don't have instructions for this yet. So you have to fill this out by increasing your list of functions to 4 different functions, including going up and down. So that's kind of your u try. Try adding the cases to deal with up and down, and by expanding that function into a list of 4 functions now. And then when you're sort of done with this, I'm just plotting a helper function to plot a line. So if you're given a list of points, it'll plot a line. It'll kind of be boring in 1D, but if you only do left and right. So finally, here's sort of the real thing with this half complete assignment. Because people are complaining I'm just putting everything here. So now you really have to go and do some stuff. So here's I'm printing the left-right walk. So I start at 0, 0, I go left. Sorry, I go right, and then I go left. So this picture is kind of boring now because it starts from 0, 0, goes here, and comes back here. So it's plotting a line. But in 2D, it'll look more interesting. It'll look like a little pattern. So that's kind of the assignment. Make sure that this blue line is now moving in the 2D grid. Okay. So 4 functions in your list. Yeah, it's a bit boring in 1D. So that's the assignment. Yeah. So here's this extra challenging assignment, right? So just imagine doing it in 3D. So now you have to have one this way, this way, this way, this way, and up and down. So which means you need to break the unit interval into 6 chunks, right? 0 to 1 over 6 and 1 over 6 to 2 over, gosh, 2 over 6, 1/3, and so on, right? So then you'll have 6 equal sized pieces, and then depending on where it falls, it should work. So all you need is just, you know, just a nice little function. See, these make left turn and make right point turn if you want. So that's already 3D walk. This is 2D walk, right? And in fact, you know, start scaling this, you basically get close to, you know, this is basically the beginnings of Brownian motion, right? So instead of going left and right, if I go up and down and then watch where this thing goes through time, that's essentially the construction for simple random walk. And then when you look at the scaling limit of it, so you know, you kind of keep doing this n times, and then you start dividing everything by n, then you basically have the primitives for what's called Brownian motion, which is fundamental tool in stochastic calculus. So it starts here. Yeah, Einstein's paper on Brownian motion, I highly recommend. The original paper. I don't know. He loses me after the first page. I keep reading it every 3 years. What is he talking about? It's a very weird paper. Anyway, it took Wiener to formalize it mathematically. Okay, that's that. So let's hit the next one. And then oh, I had some more. Oh yeah, here's 8. Okay, I haven't finished this notebook, so I think I'll probably stop up to here. So I will try to give you a flavor of what we are going to do from the continuous uniform 0-1 random variables. How are we going to transform these pseudo-random numbers into other realizations from other random variables? So that's the main idea here, right? So this is a whole field. There's a beautiful book called Non-Uniform Random Variate Generation, and that is basically the Bible, and it's free. By this other pretty amazing mathematician, mathematical stats guy, Luke DeVroy. So yeah, he says, I give anyone the permission, even without asking me, to take these PDF files to printer, print as many copies as you like, and sell them for profit. He's pissed off with Springer. But anyway, Luke is going to be in Uppsala soon. He's pretty amazing. So in fact, the last lecture I give is actually, you know, dedicated to Luke, right? This is part of this L1 school of statistics, right? So he's getting some big prize. He's also giving the Wall lecture, which is this great lecture for mathematical statistics. Happens every few years. He's giving that in one of the Slavic, Lithuania, I think. And then he's coming here for another prize for the randomized algorithms conference, analysis of algorithms conference that will be in Uppsala in late June. So yeah, this book is really amazing, and I basically have a hard copy of this. This is where I'm rolling out stuff for you guys from. So you can dive into it. Really want to get into it. Okay, so let's okay, so this is our uniform 0-1 random variable, right? It's just the density is constant 1, and the distribution function is just the identity function, identity map inside the unit interval 0-1. And this is what we were doing before. And then we kind of got a flavor for you know, what's going on under the simplest possible ones, pseudo-random number generators. Now let's do the following. So let's create a list of uniform samples, and of course we'll get different samples. So we have to, you know, understand how to fix the seed of this built-in method. right? So if you hit the doc string for the seed, it says set the current random number seed from the given seed. So in our LCG, we were doing x0 on our own as a parameter to the function. So here we want to set random seed is the call. So you can put some integer there, and then it will give us the list of uniform samples now are these three numbers. And if I ask what's the initial seed, it'll give me the long integer. It casts it to a long because, yeah, Rand is working on long integers. So now the nice thing is if I set the seed again to be exactly the same number, you are able to replicate exactly the same list, right? So that's the idea. And this is again another very nice feature of pseudo-random numbers as opposed to truly random numbers generated by some machine, because we have reproducibility, so it's easy to debug programs and things like this. So once again, we can ask what's the initial seed, and it'll be the same one because we set it. And of course, if we set the random seed to be some other number, it'll be different, right? The realization is not the same. So you use the seed to control the sampler. Okay, now we have the seed under our belt, so we always have to be precise about the seeds. So now if I have three different seeds, this one, and this one, all I'm doing is the same example from before. I just roll these things in a zip, and I want to just look at these points, right? Yeah, I'm just doing some tuple comprehensions here, list comprehensions of tuples. So about 100 numbers. And the different seeds, I can look at where they are, where they start, how they look, and then I can overlay them. So you can start seeing how pseudo-random numbers started with different seeds are kind of different. And so when you start using multiple seeds, you need to be careful about what happens to the overlay in the end and stuff. But usually, so if you want to do a bit more, you can get into random states, and there's a lot more you can dive into here. So get into that on your own time. And then the question is, what can we do with samples from a uniform 0-1 random variable? Well, the answer is we can use them to simulate from other more complex random variables, in fact, everything else. So here is our Bernoulli theta random variable, and this is our sort of basic discrete one. For the parameter theta, this is the PDF and the distribution function. So we're just coding this Bernoulli probability match function and Bernoulli CDF distribution function. Just literally rewriting this expression in a function. And then this is the probability mass function plot. So for a bunch of outcomes and the probability mass function values, we can have a function that returns the probability mass function plot for a discrete distribution. So these are just helper functions we'll use down the road. I'll just quickly walk through them. This is something handy for plotting a CDF. Returns the this should be a distribution function plot for discrete distributions. And you don't have to worry about all these details. There's a lot going on with padding and colors and all of this, but it's just some helper functions we'll use. And then this is our make freq dict. So this just makes a frequency mapping out of a list of data points. It's just exactly the same thing we did before. But this time it's using the count method. And this one makes an empirical mass function from the data list. And make empirical distribution function. And EMP, empirical mass function plot, and empirical CDF plot. So let's just run these things. We'll just see them in action. So now we can quickly do an interact, right? So basically, interacts are pretty trivial. You just have to add this at interact thing on the top of the function definition. and then it has some of the things it comes with it, right? So all of these sort of automatically gets turned into these buttons and so on. So it's very convenient to take a function and then immediately start interacting with it. So this argument you see, so when theta is half, this is the fair coin toss, right? Bernoulli half. And you can see the mass function is plotted to the left and the distribution function is plotted to the right. So of course, if we change it to values, this is what I was trying to plot on the first day. You see, it just moves around. It's just, yeah, that's basically 1.10 is not defined. Which is good. So anyway, this is simulating a sample from the Bernoulli. So how do we do this? So we have to get into this function called floor. So if z is 3.8, floor of z is 3, right? So it just gives you the largest integer smaller than that number. It's the floor, and then the ceiling is just the large, the smallest integer larger than that number. So using floor, we can do what's called inversion sampling. Right? So this is the main idea. So we can do inversion sampling from the Bernoulli theta random variable using the uniform 0, 1 random variable. So what is the inversion sampling? So the main idea is this. We introduce the inverse of the CDF. Remember, I said that if you go to, so here's my distribution function. So let's see, for Bernoulli, what's happening? Let's say theta is, let's make it half. So the distribution function will be like this until 0. At 0, it will punch a hole and jump here, right? And then it will be like this, and at 1, it will punch a hole here and jump here. Right? And then we just put these dotted lines to help us visualize. The dotted lines mean nothing. Okay, so that's what the f of x semicolon theta equals half is. Right? So what is the inverse distribution function? Right? It goes in the other direction, right? So it will take values here. So this is, say, x. X can take 0 or 1 with positive probability. Right? So it will take some u here. Say u falls here, some uniform sample. It will be between 0 and 1. Then it basically will go here and invert it. So it'll fall at 1. So any value of u between half and 1 will fall here. And any value of u between 0 and half will fall here from 0. That's what the inversion does. So that's how we can always go. Because the distribution function takes values always between 0 and 1, this magic applies to any distribution function. Right? This inversion sampler is the generic way of doing it. So if you have some arbitrary distribution function, okay, so it should be non-decreasing, whatever. Something like this, then, and it can have jumps, no worries. So maybe there's a little jump here. Okay. So what it'll do the same thing. It'll, so now we have, and it asymptotes out at 1, let's see. So it basically will take samples from the uniform, right? Be somewhere between 0 and 1, and then it'll simply get the x from here, which is f inverse of u. So that's my x now, right? So that's how I can go from, say u1 fell there and it goes here, u2 fell there and it goes there, and so on. That's how it'll invert. Okay. And this should make sense, right? If this is maybe a more complicated thing, but imagine if we have a Gaussian random variable, right? You guys know the normal distribution.
Yeah.
If it's highly concentrated, how will the Gaussian look? So I'm going to draw it in yellow. Let's say it's concentrated at this value. This is the mean of the Gaussian, right? Yeah. So let's see. I need half. So it'll kind of do this, right? Something like this, right? This will be half. And if the variance is really small, then it'll do this, right? I mean, these are actually lecture materials for later, so I might skip all of this. You just need to know this idea, so we'll do more interesting things next Friday. So you basically, let's say it's another, the mean is still mu, oops, mean is still mu, but then the variance is really small. Then, this guy will really do that, right? Will concentrate. So then what? If you have u's coming at it, the blue u's, so let's say I have u1, u2, u3, so it says the same sequence of random numbers, u4 and so on. Then, for the blues, these guys will all fall very close to mu, right? Because the variance is so tight, you see? So these samples will be very close to 0. And, the same use for the yellow will be more smeared out, right? And that's basically why the inversion works. That's pretty much the main thing you do. If you can get away with finding the inverse of the distribution function of a random variable, then you would just use the inversion sampling. And then there are other methods which you have to do when you cannot find the inverse explicitly. In fact, for the Gaussian, you can't do it explicitly. You have to do other things. But conceptually, you can do it. So that's the basic algorithm here. I'm just looking at Bernoulli. So U is uniform 0, 1. And theta is the parameter. This is the input to our simulation function. The output will be x, which will be a sample from the Bernoulli theta random variable. Here are the steps. U gets a sample from uniform, and then x gets the floor of u plus theta, right? So the floor of u plus theta is the expression for what I'm doing here, right? I take u, and then I add half to it because theta was half here, and then if u fell here, it'll jump above 1, u plus theta, but the floor of that will be 1. It's just the same thing. It's just a way of encoding that picture. Okay, so this is just more walking through the mechanics a bit. And so we can define this Bernoulli F inverse function to be to return the floor of u plus theta. And then we have the Bernoulli sample. We want n samples for parameter theta. I'm just first doing a list comprehension of random u that many times. And then I return this list comprehension, right? I can just do Bernoulli F inverse of u comma theta for each u in this list of u's I've generated. So there's nothing going on. That's my function. So I have my inversion sampler for the Bernoulli, right? This is what we were doing intuitively when we were doing the random walk, right? I mean, for the left-right part below. Because that was also Bernoulli half. There you go. So theta is 0.2 and 10 samples, and 3 out of 10 are, heads or ones. Okay, and let's try out this interact. So, yeah. Oh yeah. Okay. Yeah, I mean, this is what so now, like we were doing the same before, let's say if you make this smaller, you see that almost all of this. Yeah, it's kind of an annoying bug here. I should force the interact to only take values between 0 and 1 for theta. So you can see that, so now I'm increasing the number of simulations, and what I'm seeing is actually the, how well the empirical mass function, which is on the left, and the empirical distribution function, which is on the right, are approaching the true ones, right? So, okay. So I was just checking that simulation is making sense. And that's what all the helper functions are upstairs. They're all being called here. ECDF plot and empirical probability mass function plot and so on. Okay, so this is just sort of really going slowly into this. So let's do this other one. This is the equiprobable de Moivre theta random variable. So this is the one where when we have, say, 1 over k times, and that's the mass function and the distribution function. So we saw this earlier, and we can just recall these as it interacts now. So we have the mass function, 1 over 6, and the distribution function for this rolling a fair die experiment. Now, simulating a sample uses this idea, right? So we can still do floor, but then we just have to blow u by k, right? So u is always between 0 and 1, so we multiply it by k, so it now stretches from numbers between 0 and k, right? Then we add 1 and floor it, right? I mean, we floor and then add 1. So that's literally the inversion sampler for. So here's the pseudocode for it. You have the u, and you have the parameter k as input. We get a equiprobable sample from the de Moivre k random variable. And then what do? We take the floor of u multiplied by k and then add 1. And this adding 1 is because this random variable takes values 1, 2, 3 up to k. Just, you don't have to add 1 if it takes 0 up to k minus 1. Okay, so that should be straightforward. So all of this is clear, right? I don't have to go through these things line by line anymore. Okay. So now we have the de Moivre 10.6. So we have 10 samples from a fair-sided die already. Right, and this interact is just checking that if we do a bunch of simulations, what is the empirical mass function and the empirical distribution function looking like? So with 10, this thing is a bit jaggedy, right? But if you keep increasing it, imagine there's a true distribution function with the 1 over 6, 2 over 6 hops, right? That's really there. So this thing is just from our simulated sample. And in fact, as you increase the sample size to 65, it's getting better and better, right? So if you keep increasing it, it'll start really hugging the true distribution function. And I said that's actually sort of the simulation of this fundamental theorem of statistics, I said, which is that the empirical mass function will approximate, will converge to the true distribution function, no matter what the true distribution function is. Okay, so ceiling is just, as I said, it's the smallest integer bigger than that number. Okay, so this is good timing. So I'll finish this in the next 7 to 8 minutes, and then we will turn into a little bit of tutorial and play with the New Zealand earthquake data. Okay, and then you can, if you get bored, you can do the random walk as well, and then I can check you on my list, so you don't have to do anything. So this is the inversion sampler for continuous random variables. I already drew the picture. That's the whole idea. You just have to invert it if you can, find the inverse, and you're done. So, this is basically the theorem or the proposition. It says, let capital F of x be the distribution function, going from the reals to the 0, 1. That's what I drew here. Right? So, and let's say it has a continuous distribution function of density f. So we don't have to worry about these jumps per minute. And then we say it's its inverse is simply the infimum of the set of all x. That means the smallest element in some sense, such that f of x equals u. Okay. And then that basically is the inverse thing, right? You go from 0, 1 downstairs. Oh, wait. We should switch to this. Okay. So yeah, so basically the proof is one-liner. You know, it's just it's basically almost a tautology. So so the probability that the inverse of the random variable u is less than or equal to x is just the probability of the set you know, the infimum of the set of all y such that f of y equals u is less than or equal to x. And this is just the probability u is less than or equal to f of x. And that's just f of x. So you just literally, it's just property and definition. So if you can do the inversion sampler, you go for it. And the general idea here is always a pseudo-random number generator is producing a sample from uniform 0, 1. And then there's a procedure to give us f inverse of u. So if this procedure exists, we're done. We just apply the procedure. Boom. Yeah, this is a typo. So I should say. So now let's try this on the uniform. So we can apply this idea to the uniform theta 1, theta 2 random variable, right? So it's just the same thing. So here we have two parameters, theta 1 and theta 2. And intuitively, all we're doing is just, you know, say 0, 1 is here somewhere. So all we have to do is basically take these numbers that fall in the uniform in 0, 1 and simply multiply that by the width and relocate it at theta 1. Right? Just stretch and relocate. So, and that's what, if you formally work through the distribution function, that's what this will do, right? And here's the PDF of uniform -1, 1, this CDF, and this is what the inverse of the distribution function looks like. It's just another linear line, but with a different slope going from. Yeah, so I'm showing you the inverse now. So you basically take any values in 0, 1, and then it'll give you values in -1, 1. It's just this picture turned around. That's it. So that's your PDF and distribution function, and then we can simulate from it. So we can do this in our head basically, because u basically is going to be just theta 1 plus, sorry, you take u, which is in 0, 1, you just multiply it by the width of the interval, and then relocate it by theta 1. So that's all that we can just see immediately. Okay, and that's basically the algorithm for inversion sampling. So just do the same, and so pretty much what's happening in random when you call all these other densities, all these other random variables, which we will get into more and more, like exponentials and gammas, they are doing inversion sampling whenever they can, and when they can't, they will do very specialized algorithms that come from, say, Du Bois' book explains all of them. Because you cannot find the inverse expression for the inverse distribution function all the time. Okay. All right. So now we have we're just calling all of this, and we can just simulate samples from -5, 5. And the interact again checks that these things are making sense. So we just have one sample from uniform 0, 1, and you can change the theta to be something else. theta 1 and theta 2 be doing something else, and increase the number of samples. Okay, and of course we can always dump this into a distribution, into a histogram. So as you increase the sample size, you're going to get sort of more uniformly spread out points. You can increase the number of bins. Oh, by the way, this problem of what the bin size should be, that is the problem. Right? So this seems so simple. Like, how many bins should I have in a histogram? So what I do, I have a bunch of points and I'm creating a histogram. And this problem is a more delicate problem. So it's asking you to reconstruct the density from a bunch of points, right? And I'm using a histogram to kind of eyeball it, right? But look, if I made the sample a bit smaller, it's too much, you know. And the problem is if I have let me make just 100 samples or something. So if I have just a few samples, say 50, and then if I have just a couple of bins, oh, probably there's not much about error checking here. So you know it looks very undersmoothed, and if I make too many bins, it gets very jagged, right? So for any n, the optimal number of bins is it's called a smoothing parameter. And that's, in fact, the whole topic of the last lecture on June 1st, right? How to do this. So I don't know, a lot of you want to come to the lecture. I don't know if you really want to. You're welcome to, but it will be just Blackboard, and it will be just about the smoothing problem. And but yeah. I think SEB is paying for FICA for the pure math part, so that's good. I thought that'll be nice. Okay, so that's basically it. I'll add a few more examples. We may not get into them, so I'll introduce the exponential random variable. So do you guys remember the exponential density? It's one of the most basic ones. Okay, let's get into that. Exponential. So uniform is important, right? But the uniform theta 1, theta 2 is also very nice. But maybe the next most interesting continuous random variable is called the exponential random variable. Okay. So we say x is exponential random variable with parameter lambda, right? It's called the rate parameter. If we usually subscript by x. Right now it's okay. So then we say if f of x semicolon lambda, is the parameter, is going to be lambda e to the minus lambda x. Okay. So let's just work with the density. So the density looks like this. So if say lambda is 1, it'll kind of start with 1 and, you know, decays, right? So it'll look like something like this. Right, and if lambda is like, say, bigger than 1, then it starts higher and it'll look like this. I mean, it'll decline faster. And of course, the area under the curve is always 1 for any lambda, right? And if lambda is like much smaller, like it's going to really take a long time to fade out. So again, the area under this curve will be 1. So this is a very, very important random variable because it's kind of what's behind making, you know, it has this property called memorylessness and so on. So it's very useful random variable to have, especially if you want to ignore a lot of the details. And often, like the earthquake, the time between earthquakes is really well approximated by this random variable. Right? If you look at the inter-earthquake occurrence times, right, that is usually well modeled by this. So, and then for so what the rest of the notes will go is it will give you the distribution function for it, the inverse distribution function for it, and then write down the simulator for it and stuff like this. So you can go through that on your own later when I fill out the notes. And just because we're kind of running low on time, I want to get to more interesting concepts now. And then the other random variable is called the standard Cauchy random variable. This guy is also really interesting. Recall from memory. Standard Cauchy is double exponential, right? Can someone look up in Wikipedia for Cauchy random variable? And tell me if I'm wrong with my density. So let's see, what is this? Oh yeah, the Cauchy random variable is really interesting because it's something like, is it e to the minus, well, it's a double exponential, right? So it'll, what is it?
I think
Can you tell me the expression?
probably this is not a Cauchy, because the Cauchy is a division between. It's also the distribution of the ratio of two independent, normally distributed random variables.
Yeah, it should have some absolute. Where is it?
I think I'm on the wrong one. We're not talking about.
Oh.
That's totally different.
Oh, sorry. So I think I'm. Oh, really? Oh, God. Okay, no, this is Cauchy. Okay. All right, doesn't matter. So I will introduce the Cauchy random variable formally later as well, because that is going to be the counterexample to.
Maybe you're meaning the Campbell distribution?
No. Okay, so let me see. This is Cauchy. So. Oh. Okay. Yeah, I don't know. Okay, doesn't matter. So there is a couple more random variables. I have to look at what I actually wrote. I think I'm thinking of what's called a double exponential, maybe. Anyway, I haven't finished all my notes. Okay, so there's something called the standard Cauchy random variable, and it's interesting because it doesn't. It's a nice counterexample to some basic limit laws, right? The sample mean won't behave in the same way because its expectation doesn't exist, right? So it's just a little example we'll have. And then what I think so I'll let you guys kind of look at this in more detail, and then next time when I come around, we will get into convergence of random variables. So these are very important concepts. I mean, the main thing about this density is basically its expectation, does not exist. Okay, so when you start, you can work with them too, but then you can't say a lot of limiting results. So I'll get into. We'll just quickly look at limits of real sequences, deterministic sequences, and then we look at limits of random variables. Right, this is the beginning of math stats, right? And probability. So limits of random variables. How can we talk about limit of random variables? Because this just means like I have a sequence x1, x2. So this is a deterministic sequence. So it's a real line. So here's x1, here's x2, and maybe they're just converging on some limiting value, say x infinity. So you talk about limits this way, right? I'll remind you guys quickly what that is. And then, but how do you talk about limits of random variables? This is not a easy concept because every time you do the experiment, the random variable takes a different realization. So then there are different notions, So you can talk about convergence and distribution, convergence and probability, and things like this. We won't do more than this. There are other notions, and then this will give you an idea about what it means for the real problem, which is inference. You really need 2 full days for inference. But I'll quickly get into this. So here the problem is backwards, right? So I have my data, x1, x2, say, and this comes from some density, right? IID, that depends on some parameter theta, but you don't know theta. And your goal is to take this sample, this is little x1 to little xn, take the sample, and then try and estimate theta, right? So this whole way of getting the estimating theta is, this is called an estimator. And that itself is a random variable because every time you repeat the experiment, you get different estimates of theta. right? And this is parametric inference. So parametric inference basically has, the main school is called likelihood, right? So it's called the likelihood principle. And there is an estimator from this school called the maximum likelihood estimator. Right? So what I would like to do, maybe instead of all the syntax now, is I'll try and show that the maximum likelihood estimator is what's known as asymptotically consistent. Right? So these are all very important concepts. So what is asymptotic consistency of an estimator? Asymptotically consistent. That means, the random variable, the estimator, which is now trying to estimate theta, right? What is it? It's going to have a distribution function because it's a random variable itself. So somehow, if the parameter we're trying to estimate is just a real number, right? So let's say Bernoulli, right? Theta is some unknown theta, so it's the truth. And we know it's some number between 0 and 1, right? And what we want is our estimator will have a distribution function, right? Because it's a random variable. So there's some omega under the hood and something happens and we have a Bernoulli measurement, right, x. But we're measuring x again and again. So maybe x1 fell somewhere between, x1 can only take 2 values, right? Maybe x1 went there, x2 went there, and so on. But if I repeat it, it could be different, right? So I will have an estimator that will somehow converge to the true theta in some sense. So that's why we need the notion of an asymptotic consistency means as n goes to infinity, right? As the number of data points go to infinity, the estimator will converge in some sense, some squiggle arrow, not in the sense of real numbers, to the true theta. Let's call this theta star, the unknown thing. Right? So that's basically guessing the bias of the coin from just looking at the outcomes of the coin, right? And this applies to arbitrarily complicated situations. Oh, I forgot to bring the double pendulum. Okay, I'll bring that. So in the double pendulum, we can just do that and do measurements, and we'll get timestamps. And so now, what is a double pendulum? Theta is what? Theta is now some element in maybe up to 7-dimensional real space. What is this? G, so-called gravity, right? Some number around 9 point-ish. We don't know. So this is some number. And then, there's the length of each arm of the double pendulum, the center of mass, the friction. These are all parameters, right? But what is the model? The model is basically this so-called Euler-Lagrangian model. This is a differential equation. That only gives you deterministically how this thing moves for particular values of various unknown parameters, right? Up to 7 of them. But the way you add probability to it, there are in fact 3 schools. And these schools actually literally wage war on keeping each other at bay, right? This is happening in real time right now, right? I'm talking about various navies, right? So many schools. The simplest one does this, which is good enough for lots of stuff. So it'll take the trajectories of the double pendulum, right? So this is theta 1 and theta 2. Okay, so this is say 0 to 360 degrees. And this is time, right? This is another trajectory for the second arm. So it'll take these deterministic trajectories for a given theta by doing the ODE, the ordinary differential equation, integrating it, getting the solutions. And then it'll add some Gaussian noise around it. So, that means, the actual observations may not be exactly like that. It'll be kind of around it. So it'll add a Gaussian noise. And then it'll try and basically do a least squares fit. It will try to find the trajectory. It'll try to find the parameters whose integrated solutions are closest to the observations by minimizing, because the actual data points may be like this. So it'll try to find something that minimizes the sum of squares. Just like we saw in regression, it's exactly the solution. And that actually is the maximum likelihood estimator for a Gaussian additive noise added deterministic differential system. It covers a whole class of problems. But so anyway, that's parametric estimation in kind of a nutshell. These are left to your imagination. I'll just focus on basic concepts for Friday. Then I guess the other thing I would like to cover conceptually very, very important is non-parametric estimation. So now, so non-parametric, I already told you, estimators. So here, here, we didn't know what theta was, but we know theta had only finitely many dimensions, right? It was 7 unknown numbers, okay? Non-parametric estimation, we have uncountably, infinitely many unknowns, okay? And the simplest example, again, we saw simulation today. I already said, if I have a bunch of samples from IID, from some unknown distribution f, and this f lives in the set of all possible distribution functions, right? And that means, the densities are L1 basically. So then the question is, just from the samples, what do I do? So I have a bunch of samples, and so then what I do is I basically order them. That's why we saw order statistic as one important statistic. And then all I do is I just go jump by 1 over n, jump by, another 1 over n I added. So I get the step function, the empirical distribution function we just defined. That becomes your asymptotically consistent estimator for the unknown f. So the unknown f could be something, whatever it is. We don't know what it is. But the beauty is, as n goes to infinity, the distribution function, so the empirical distribution function we already defined, fn of x. So x is now a vector, right? Sorry, fn of x is a function here for some other function. So this is the jump function, right? So this thing will converge in some sense to the unknown distribution function, say f star, no matter what it is. So that's basically non-parametric estimation. So ideally, next week I should just kind of let you guys look at these mechanics later, and then get to these two before lunch. I mean, concepts, right? Because I just really want you to get the basic concepts down. And then if you can get to these two, then after lunch, because 3 o'clock tomorrow we'll be done. So after lunch, I think what I would like to do is hypothesis testing. But anyway, I'll just do what we can, right? Because it's finite time. So hypothesis testing. So again, there's parametric and non-parametric. So parametric is basically, just like parameter estimation, you can in fact turn a maximum likelihood estimator into a hypothesis test. So I'll give you the basic idea of that. And non-parametric. So this is what a lot of these guys are doing, in the industry. They call this A/B testing these days. So this is basically, a bunch of users are clicking some things, and then you want to know if you change some actual feeds to them, will their click rates change, for example, right? So that kind of non-parametric testing is you're making very little assumptions about what is the true behavior of customers, right? So once again, this is the other main thing in statistics. And I think the last sort of notebook will just get you to Markov chains, like very, very simple 2-state Markov chains, like dry and wet. And we can look at some weather data and get the actual data for this. And then how you do, and these are probabilities, right? So P11, P12, and so on. And then we actually get measurements of days, whether it was dry or wet, and so on. And then from the consecutive, the transitions, how many dries became dries and how many dries became wet, you can get the estimate for these, PII hats. And that's basically non-parametric estimation for Markov chains. And hopefully that will be warming you up for quantum statistics lecture, right? So that's officially part of this course, business bonds lecture, the colloquium. And then I think there's cheese and wine after that too. So yeah, I mean, we have 12 minutes, so let's see if we can get into the parsing problem. So okay, so we need to have a chat, because I'm kind of because I'm trying to write a grant for Tuesday. It's due Tuesday. Yeah, and then I actually have a job interview. So it's getting quite tight, but I think we can kind of.
It works because we did it before.
Yeah, exactly.
Association studies running first, it also works. The only problem is Adam, but I have not spent much time.
Don't worry about it. Just go through all of that much slower, because we'll have like more mathy students who don't know too much about sequences. So you can take the app and all of that and really go slowly. Like I also want to really understand how the fragments. So the first half, I think I'll just do a Blackboard lecture on holistic.
You can also use the site called decay. You
Yeah.
can have the partition model with some colors and
Oh, right.
visualization.
Yeah. Okay.
Yeah.
Yeah. I'll. Sure. I mean, I'll try to.
I don't know if it's
Yeah.
it's necessary.
No, so I'll probably do just Blackboard, not because I mean, yeah, exactly. Yeah, exactly. So we'll do that. I mean, I'll see how it feels. I was gonna do MS. And, well, yeah.
Yeah, but something can already plan to before the lecture.
Yeah, exactly. I'm sure we'll meet on Thursday. Yeah, see. So, has anyone made any progress?
No.
Yeah. Well, I don't know. What should we do?
Read the CSV file.
Yes. How do we do that?
I read it.
It's not working, or?
No, I read it. With open.
How do you select only the longitude, latitude, etc.?
Okay. Well, okay. Okay. Let's. I don't know anything, right? So what are we doing? Okay. There's this file called data, right? So what is this? How do I read it first?
So with open and then the link to the file as F, for example.
Open
With
yeah.
space open.
Oh.
And then braces, put the link to the file.
Oh, the length.
The link.
Oh, okay. Okay. The yeah, where it is.
Name or,
Yeah, where the data is.
yeah. The CSV.
Okay.
And then after the bracket as F or X or whatever. As AS F
Okay.
colon.
Okay.
Enter and
Okay.
reader equal F dot read and bracket enter. Exit enter. And then exit this tab.
You mean execute it or?
You can execute it, and then you'll have the reader as a text file, and then as a string, and then you split it to a list with.
So what do you? So you're saying let's.
So now you'll be with yeah, exactly.
Yeah.
So
Next plot.
Data list or list equal reader dot split at every new line.
Like this.
Yeah. So now you'll get every line as a string.
Okay. So let's do that first. See what happens. Something happened. Okay, that's great. So I don't know what's. Oh, it's a list, right?
Yeah.
Okay. So that's your first header. Okay, so what I want is, so it's clearly broken by commas, right? So I want to split this.
Yeah.
It's very easy.
Oh, make this bigger. Yeah, sure. I mean, I'm just doing what this guy's telling me, right? So, split by comma, right?
Yeah, that is your
So I'm going to call this my data row.
What do we want to do exactly?
Well, okay, we have to grab the, so you see, this is going to be my, so we just have to grab the right columns, right? So this is going to be my, so you know the public ID event type. Origin time is the third one, right? 0, 1, 2. So origin time is this timestamp. So I want 0, 1, 2 is timestamp, and then I want data row of what do we want? Longitude, right? So that's 0, 1, 2, 3, 4. 4 data row of 5, 6. I want the magnitude and the depth. Okay, that's what so that's the strings I want to start casting into the right, whatever, floats or, I mean, this is a timestamp, right? So, I mean, I haven't descended into like, there's fancy ways to like directly deal with timestamps in Python. So what I'm going to do is ignore the timestamp for a sec, just because I kind of don't want to deal with it right now. So I'll just look at lat, long, and these are all numbers. So I guess we want to see if we can, you know, cast these into doubles, right?
Make an array, formulate a list, sorry, where you have tuples.
Yeah.
And each tuple, so you iterate in a row and then take the fourth column from the split.
Yeah, I mean,
that's
yeah.
what it will be.
So what do you, so you want to come and do it here? Yeah, we should learn from engineers, right? I don't know what, I was going to do something, but you should do, yeah, just watch the. Yeah, you've got only 3 minutes, man, so solve the problem.
So I need a tuple of, let's say,
yeah, I've got too many things. So. Don't know something. Yeah, that's good. I don't know. Probably. It's gone.
So here is 4 minutes.
Oh, okay, that's what I was gonna do. Okay, but I was gonna, you know, cast that as a RR or something or float. See what happens. If you do it.
Yeah, maybe it will double. Float.
Yeah, you can just float everything, right? I mean, you can even do float of. Data list of.
But this is a problem.
Yeah, just do data list of 1:10. So it's first 10 guys.
1:10.
Yeah, 1:10 because let's skip the header element. Okay, so that'll give you a tuple.
That's a problem because we need here to split. And you need this comma here for every one of these.
Oh, okay. Oh, this okay. But that's bad, right? It's going to split every time, and then anyway, it doesn't matter. It doesn't have to be efficient. I was just going to copy that row and then do a for loop and just do castings.
Yeah, you can do it.
Yeah.
I don't know if you can put the split here. I would try actually.
Yeah, but also like this logic is like you every time you take the thing and you split again and get the third.
I'm not quite sure that you can put it here, but maybe.
Yeah.
I don't know. Maybe I need to put another split here. Hopefully this will work.
Yeah.
Yes.
Okay, cool. So that's it, right? So then if you just do, you know, these are 3 points. So now if you do points, just do outside points. and dot show. You can just see them in the box, lat, long, and depths, right?
You can convert it to float.
Oh, yeah, well, still it's here. Okay, right. Yeah, so now you have to float it. Yeah. I mean, okay, let me, you know, in less than 1 minute, like, so what I was going to do is something simple.
You can define a small function which takes a string and converts it.
Yeah, so, you know, so this is what he's doing, right? So I can do my data, you know, I can turn this into a list, right? So this is, and then, so let's see. For data in data list of 1 through 10. Okay, so now I have a little for loop. So now this will be my data. Okay, and then I'm going to do, say, my, you know, this my data is just data row, these things, right? And then I was going to just do some comprehension, right? So I'll say my float data is equal to, will this not work? Float of x for x in my data, something like this. And then I have to start accumulating. No, I know. Done. I'm not done. So just hang on. So my data accumulator list. Okay. So then this is what you're saying. So Control V, append. Will this work?
Why don't you just convert when you do my data?
Oh, sorry. Okay, I don't know if this will work here. Okay, there you go. Invalid literal for float. Okay, I did the date. How did the date come here? I thought I.
Because 2 is the date.
Oh, 2 is the date. Crap. Oh, right. I don't want to. Right? That's the whole point. Okay. So let's get rid of that. Okay. So now, do I have something?
No, it works, but you need to print it.
Yeah, I'm going to get rid of yours because I don't like it. So, you know, I don't know. This is not. Do you have a better way, Lee?
Not really, but instead of doing this comprehension, the floats out of the complex data.
Oh, okay. Yeah, you want to write float. Okay, I don't want to write float. I mean,
I want to use pandas.
okay. Yeah, you can use pandas. We grew up into pandas, right? But you guys know Spark SQL, so.
Did you mention that there is a CSV module?
I know. I didn't mention. But,
I mean,
well,
it's a good
I
exercise,
understand, but the whole point was to
but-
like keep a little bit low level. I mean, so we just wanted, and that's what's going on in these modules, right? So, and remember, in the other class, we were just like using everything, all the built-in functions. I mean, so this is, you know, and if I turn this into, instead of that, if I made a tuple of it, then it's a little cleaner, and so now I should be able to pass this to points, right? The points 3D, and just do. Oh, that's interesting. What is it? Points maybe? Okay, there we go. I mean, all right, we're like 5 minutes late, so just to, yeah, I mean, you can do other things, right? So you have all the other functions. So I don't know if this list comprehension will work all the way down. I have no idea. But yeah, if it does, then 1, 2.
Double colon.
Is it double colon to go all the way to the end?
Yeah.
Oh, sweet. Yeah. Okay. Yeah, I would be surprised if that works. Yeah,
So maybe remove it.
this index out of range. Well, anyway, I don't
Yeah, because
remember.
at the end,
Do you know how many it had? That certain...
-1. So you write -1 to drop the last
Oh,
one.
true. So I can
Or
go
-2 or something.
-2.
Yeah.
Worked. Oh, there we go. What we have here. It's going to take a while.
20,000.
And it's a whole year of earthquake, latitude, longitude, magnitude. Oh, right. This is kind of bad because you know why it's bad? Because I don't want this, right? I actually want this to be just 3. Probably crash my stuff. But you know, I want this to be only 3-dimensional, right?
Look behind.
What happened? Oh my god! Yeah. Yeah, let's interrupt the kernel. But anyway, you get the idea. So you can start doing other stuff with this and, you know, do a few things and maybe show me sometime before June 4th. We've done some stuff. And see you next Friday.